Okay, hello. Uh, Welcome back after coffee break. I hope all you got energy with the coffee and cakes. Now it's time to start troubling our morning speakers with all the questions related to fifth force and Lorentz violation tests, please. Uh, we can just.
In terms of screening. So you basically got so you said that if you screen the fifth force solar system scales, then it is automatically screened on galactics. And this I don't understand.
What we did in the first paper was to look at various bodies, including the galaxy, and check the screening criterion. So for the chameleon, I'm pretty confident that you first test the moon and check it's screened and the sun. That the other bodies in the solar system will in the galaxy will follow. I actually wondered about globular clusters because my understanding of a globular cluster is that it doesn't have dark matter, which I don't understand why. Is that your understanding, by the way? Yeah.
Because again, it seems to me that you want screening at high densities.
Yes.
And so, since the density in the globular cluster is higher than the density of a galaxy, it seems to me that if things are screened on the galactic scale, then we have to be screened.
I think you're probably right. I can't remember what the density of the globular clusters are. I know that with in the paper Brax et al. That I put up in 2004, we checked the galaxy was screened. So with the chameleon type models, then the screening depends on the ambient density. So the chameleon becomes massive and in a dense environment and is massive enough in the galaxy. For the sun, we quite literally did included the corona and all that, and the density is lower there. So we did check the screening completely in the sun.
Yeah.
This is related to the symmetron mechanism, which I actually had never studied. So is it true that you have an effective potential which depends on the density?
Yes.
So this is a general quantity. This is very interesting because in order to justify that, you're not doing finite temperature field theory, you're doing something like plasma. Now, there's a connection with topological defect. So the standard particle physics model has a complex scalar, complex doublet. So it has four real scalar fields. Two of them are charged, two of them are neutral. The double web potential. So if you do exactly the analog of this symmetron analysis, then what you will do is you will induce an effective potential for the charged scalar field. And that leaves you with a vacuum manifold S1, which means by this mechanism, you will have scatalized strings in the standard model. This is the electric Z string, and this is something we've postulated a long time ago. So this is an interesting relationship between the symmetron mechanism and this stabilization of embedded defects.
Well, if you at high density, you're in the symmetric phase. So at high densities, you won't have strings. You get them from the breaking to the Higgs type potential with the standard argument of Tom Kibble, that is. I
thought that temperatures lower than the phase transition, you have a negative magnetic capacity. It's the coupling of the charge state and quantum, which are given away the density. So this is an interesting analogy.
yes, it's analogy. I don't know.
Who knows it? There are two papers by Nagasawa and myself.
Okay.
Proposes.
Now, I must say, it is a Higgs potential, but I've never really considered cosmic strings in the symmetron model.
This is not where I'm going. I'm just
Okay.
Analogy.
Yeah. Okay.
Any more questions or follow-ups? Then I will take the opportunity to ask questions. Well, and I have a question. You mentioned in one of your slides, this potential, runaway potential is comes from compactification of 10 to 4D, and how robust is that? Are there any debates on this compactification and getting this potential? So,
Which potential was that? Was that the dilaton potential?
yeah,
Okay. I thought that was well known until I sat down afterwards and Kelly asked me, where in Green, Schwartz and Witten is that? So I'm sure I found it there at one stage, but it's also in Veneziano's paper, and I believe that Veneziano certainly knows. Gasparini and Veneziano certainly know more string theory than I do, particularly Gabriele. And if he's got an exponential potential, then so be it. I don't know how robust it is because I'm not actually a string theorist. But if some string theorists say this is what it is, then, you know, then I presume that one can take that. So it was string inspired. When I wrote down the dilaton potential, well, Gabriele wrote it down first. When I essentially stripped out some of the things that Gabriele had and just had a sort of exponential type decaying potential, I thought that was string inspired, but I might be wrong there.
Before the dilaton start from 11 dimensions, it's just part of the metric. And as you dimensionally reduce, you develop these generally called duality symmetries, which the simplest one is in 10 dimensions, it's just R, not much of a group, but that's what it is. And if you parameterize it as an exponential of a scalar field, that scalar field shifts. But anyway, that's where your exponential comes from. And then it multiplies something like a form field string. And if that develops a value in the background, what's left over is exponential. But that's for the dilaton, it's natural. It wasn't so clear to me where it's a pseudoscalar little friend gets it.
Well, you're happy, aren't you, that the supermultiplet consists of a scalar and a pseudoscalar. Now, the axion part has come from work of Burgess and Quevedo, and probably many others. And I think it might be a bit more phenomenological than reducing from 11 to 10 and form fields. And I think it might be more phenomenological, but I don't actually know. I think I might leave the loop corrections to my string theory friend who is sitting.
Yeah.
I don't know point. You mentioned that some of the models that you're looking at don't have a Lagrange formulation. First of all, why? I mean, in general, for the source breaking theories, you think you should be able to write it. But second, if you don't have that, what's your dynamical principle that gives you equations of motions and correlation functions?
That's a good point. So for the breaking, you can do that. So I showed you an example that does it. For the deformation, this is still not clear how to do it. As I said, there are a few issues. One of them being that you do not have standard conservation laws. So you will need to encode that in a Lagrangian theory. You do have a deformation of the concept of locality. So that is also something something problematic. There have been attempts at doing field theory. So people are working towards that. Some attempts, for example, rely on a non-commutative field theory, introducing deformed multiplication between fields to encode this non-commutativity. It works for some models better than others. So there is work towards this, but at the moment there isn't an established way to do it. So so it is an open question at the moment. Yeah, so the dynamics is still an open question. So you hopefully at some point we'll get there. It may be that again, this only makes sense in this specific limit where you're considering point particles, and when you want to go to something more towards the field theory, you have to do something a bit different. There are also good reasons to expect that you will need to go to a full phase space picture. So not having field theory on space-time on its own, but at some point you will have to do something on phase space, because you have similarly to the mixing between space and time that you have in special relativity, here you have a mixing between the space-time and the momentum space. So this may be one way to go in trying to do more complete models.
Look.
Yesterday, because I remember once we were discussing last year, maybe also with Patrizia and today about some approach there is no commutative geometry. You can have some Lagrangian description, but in terms of non-local kinetic terms in a local interaction.
Yeah, this is what I was mentioning earlier. So when you do this non-commutative field theory, because you have a modified product between fields, usually this modified product contains derivatives of the field. So you go higher order derivative. And this is what introduces the non-locality.
Is this like an effect Lagrange or is it domain Lagrange that is associated with this?
I don't think this is fundamental. I think this is a description in some regime. For example, you're not considering any, I don't know, dynamics of space-time. Probably when we want to go to the full thing, you have to consider some sort of dynamics of the phase space. I don't know. I mean, there are many unknowns there. So I would consider it as an effective model that works in some regime.
Well, in this sense, there is a comment. If we implement Moyle-like non-commutative product, we in principle can create our theory, our Moyle-based non-commutative theory as a fundamental one. However, in this case, first we have the problem is how to create problematic infrared singularities. Well, it is more or less solved with use of supersymmetric extension. And second, perhaps for such an object that Moyle product, there must be some justifications. And the main problem just perhaps existing just up to now is how to generalize it for the curved space-time. I heard from one communication of Charles Lane in the event organized by Alan Kosterevsky with collaborators that perhaps in the gravity, the Moyle product should be the usual one, but in principle, it is only one of the steps. Whether this will be the best solution, etc. Just now, up to now, nobody knows yet. But in principle, nobody forbids to create Moyle-like non-commutative theories as fundamental ones. As for other basis for non-commutativity, well, it is a problem to think. I think so.
I raise my fingers. I have a follow-up on this. So, Julia, you presented this non-commutative algebra with a commutator between x0 and xi.
Mhm.
Well, usually in quantum mechanics, time is not an operator, and Pauli's theorem clearly says time cannot be an operator. And also, Wigner proved that time reversal is anti-unitary. So how can you allow this, and what is the logic behind? And follow-up is, okay, if from following your cube, if you say in quantum gravity regime, time can be an operator, you go to low energies or whatever the limits you take, you have to recover quantum mechanics. How can you recover that? Time is not an operator, but operator at very high scales.
Very good question. Yeah, when you do this non-commutative spacetime, you are promoting time to an operator. It lives together with the space coordinates on an Hilbert space. So usually what works there is to approach things using this covariant formulation of quantum mechanics that allows you to treat space and time on similar terms, and then you go to the physical Hilbert space, and that's where you see that the usual quantum mechanical time evolution. So that could be one way to look at this. Concerning how you recover standard quantum mechanics, well, eventually you are going to be in a limit where the non-commutativity is not relevant any longer, the space-time non-commutativity. And you're left with the...
But still changing the time operator character, so that is something...
Well, you may argue that it is quite non-analytical as a limit, even though formally it is just taking your space-time non-commutativity parameter to zero. But I agree that there is a big conceptual transition there.
Okay. Any more questions or follow-ups?
Mr. Gubitosi, I'm not sure I understood, but I remember there was a slide where there was the deformed inspection relation for a particle, and you say that you can make this particle travel on a Minkowski background or a Friedman background, and maybe if you are considering the solar system or the particle which is traveling on
intergalactic scales. But so my question is, this is a deformation of Lorentz. You say your framework is that you are taking the first order correction on the physics we know, and this is not full quantum gravity. But so first, if I understood the slide, and the second question is, but then if you want to push this theory to your to the full quantum gravity rating, so the deformation of Lorentz and so on, and so you go like to the vertex of the cube you show us, following this kind of. Can you be sure that then it still makes sense to expand on the physics we know, or like the deformation of Lorentz, if you take it for space-time itself, will bring something that I do not allow you to consider a particle without deformed dispersion relation on a space-time that we know, which is
well, of course, that picture at some point will break down. At some point, you will have to have. I mean, if you think about what could be the full quantum gravity theory, that is a theory of quantum space-time interacting in who knows which ways with quantum matter. Of course, from there should exist a limit where you can describe the quantum features, how quantum features of space-time act on matter. So in the end, effectively, what could happen is that you have this modification of the dispersion relation, and you describe the geometry as a smooth geometry. But of course, this picture at some point has to break down if you want to go to the full thing.
The deformation of Lorentz for the space-time and the deformation of the dispersion relation, they cannot be separated. Like you have a GR space-time and then the particle which is already a deformed space-time relation.
No, it's not that you have a. So the picture is that you have a smooth space-time, meaning that you don't feel the possible fuzziness or discreteness of the space-time that you may expect when you go to the full theory. So, well, there is the famous example of the Brownian motion. Okay, so Brownian motion is motion of a particle of dust in water, and you see the particle scattered around. Okay, what is happening is that it is feeling the collective effects of the motion of the atoms of water, and the net effect is that you see the piece of dirt scattered. And that's in fact how people realize that water is made of atoms. You can have an analogous picture here. There is some underlying structure of space-time which you do not see, but you can still describe motion of objects, of particles on this space-time that in general will not be what you would expect on a smooth geometry. Okay.
Any other questions or follow? By the way, you both are allowed to shoot each other, so please feel free. I mean, shoot each other with questions, not really. Yeah. If no questions, yeah.
The question is about test of the Newton's potential of Newton's law at short distances. I think the best test so far was by the group of Alderberger, I think, from Seattle, and they reached distances of like 50 micrometers. I think. Is there any plan for the future to some new experiment that wants to go like below these scales, or there is nothing that is planned at the moment?
Don't really know. Yes, you're right.
Sorry, to microphones.
On? Oh, it was on when I had it and I switched it off. I don't really know. You're right that Edelberger's got a lot of those constraints. Actually, it could be that there are Casimir constraints because you can do an experiment measuring a Casimir type experiment. It's the one I put up the other day.
What distance they reached? What distance they reached, like between the masses? You know what?
It's on the micron level,
Micron, still micron. Okay.
Yeah. Which is amazing.
Yeah.
Sorry, did you say micron? I did.
Micrometers.
Yeah, micron.
And is this published?
The review is published. Now, it gives results. I mean, it's more than I can summarize in a sentence. It looks at, one over R to the power, with various results per problem. It's a review article. I haven't had a chance to sort of digest the whole thing. But there's quite a lot in it.
Because the experiment I know would be okay. I'd quite like to see. I'd quite like the reference to that, if possible, please. If I can find it.
Because I know people, over coffee in Dubna told me that they were doing that sort of thing in Dubna and other places in Russia. And then because we talked about it, I found this most canonical review from maybe 2020, not long ago.
Okay. The experiment I know is the experiment of Decker. And I think he probes distances between a sphere and a plate between 15 micrometers and 65. And which is a bit more than Adelberger's. I think off the top of my head, I think that's the what it is, but I would need to check the details.
Berger reached 52 micrometers.
Yeah,
If it's people from Russia, that's even less than that would be nice.
that would be amazing.
I have kind of follow-up question to Anna. So you mentioned about solar system tests, but what about, for example, testing fifth forces with binary systems, binary neutron stars? Did you study them? Are there any severe constraints from there?
How long do I have?
Well, as long as you want. Maybe short answer.
I mean, there's a vast number of. Hang on a minute. Is this? Well, I've just knocked my water over. We were both in Frascati. Is that correct? I presented pulsar constraints.
It was 1 year ago. I forgot. Sorry. Yeah.
Yes, of course. There are two pulsars in particular with excellent data. There's the Hulse-Taylor pulsar, and we've been observing this for over 30 years. And there's a more recent double pulsar that is giving really accurate data because there's two pulsars there. And you can extract the various astrophysical quantities and then take your favorite model and make predictions. What we actually did is taking a general scalar tensor theory with the most general coupling to matter, containing both a conformal and a disformal coupling, and then extracting the astrophysical quantities to test against well, we did it with various pulsars, but in particular the Horst-Taylor and the double pulsar. And so, yes, you can do that, and that just constrains the parameters. You can also look at the tip of the red giant branch, which was done by Jeremy Sechstein. And there's a review by Claire Burridge and Jeremy Sechstein a few years ago, where they've got a lot of astrophysical tests, not binary pulsar, because they wrote the review before that was out. But yes, you can do.
And did you constrain your axial dilaton model with those pulsars?
Oh, the axion dilaton model has only just been finalized. The paper hasn't, the paper has not actually been finalized yet. There is a draft paper. It's not published. So the answer is no.
Okay.
I mean, I thought about it, but of course, the other thing you can do is you can constrain chameleon models using using the sun, actually.
Just a different thought. Like, when you mentioned chameleon models, you do the screening for the solar system, but for example, on very large scales, we have dark matter halos and subhalos. Do you think that any kind of screening is required or between subhalos and big halos? I don't know if my question is making sense.
This is almost what Robert asked.
Yeah.
What we did in the first paper was to check the screening criteria about various objects, including the moon, the sun, and check the galaxy was screened. What I don't think we did, although it's a long time ago now, was to say, well, we've got the stars and stuff inside the galaxy, and there's a dark matter halo. We didn't actually break down the galaxy into a dark matter halo and the stellar part, but we just took the density of the galaxy as whatever it is and checked the screening criteria.
Okay. Any follow-ups and questions?
Is there a specific argument to say that at a certain point the particle is still Lorentz? But this time metric is not Lorentz, but it's just because I'm assuming that this Lorentz deformation holds also for the space-time itself.
Well, it is a Lorentz deformation of, well, first of all, space-time in itself is a bit of a very abstract concept. You need to put something in it to probe it. Okay, so in this discussion, you can think about it as sometimes I think about it almost as a mathematical tool that you have, but what you care about is the signal that is propagating in it. So the signal that is propagating in it, usually you would expect it to propagate according to special relativity. And in this case, you are seeing that it is not. Then, of course, we want to do propagation, so you need to have some notion of space-time underlying. And yes, you can use, for example, Minkowski, standard Minkowski space-time. But I wouldn't say that I'm thinking about a way to phrase it. Yeah, in the end, probably the complication here is arising from the fact that you should really think about the momentum space of the particle as the fundamental entity rather than the space-time. Okay. And that thing indeed is deformed because you have these deformational symmetries and you have curvature on it. And then space-time at that point is just the cotangent bundle of this curve manifold that you are considering. If you want to go to curved space-time, then things become even more involved, and this is where phase space geometry that also Stefan was mentioning earlier comes into play. So, but that requires to go beyond the usual description, the Riemannian description of general relativity.
So I see it's related to pushing this scenario to the full quantum reality.
I don't know why you want to push it to the full. I don't want to push it to the full quantum gravity regime.
In the during the talk, there was a discussion about are you pushing this violation to the
yeah, I mean, I don't know what happens in the full quantum gravity regime. This you should ask to people who are working to build a full quantum gravity theory. Then the question is, once you have the full theory, how do you take the limits to test these physical regimes? But I wouldn't, why do you want to push it all the way up?
No, because I was thinking that the Lorentz deformation seems a fundamental thing that we expect you can push and hold to the vertex of the cube. Since
one would need to see, but to see how this is related to a fundamental theory. Yeah.
One way to see it is imagine you have a full non-perturbative quantum gravity where you have a discrete structure. You don't have space-time. You have to do a classical and continuous limit to get right? So in a certain sense, it may be that is the scenario of deformation can be the case in which you do the continuous limit first, but still you have somehow some parameter which is defined by the quantumness of the space-time. And given that you want to build everything in such a way that is always without the preferred system of reference, then you have this deformation. In a certain sense of what it would be that when you write the dispersion relation, you write G mu nu of kappa nu equal m squared. Normally it's the way we write the dispersion relation, but now G mu nu, it would be G mu nu in curved space-time of x, but also k, in the sense that it depends on which scale you prop space-time, because the scale are very long, you see just the classical space-time. If the scale is starting to be too close to whatever is the deformation parameter, you start to see that the space-time is not the same.
Yeah, and eventually you will not be able to write that thing any longer in a meaningful way. Eventually you go to smaller and smaller scales, and you will not even be able to write that in a meaningful way.
You go beyond the continuous limit and you have a pure discrete structure, then it doesn't make sense to talk about the deformed Lorentz group.
I have a follow-up on this since there's a lot of mention of curved space-time. So I'm curious if you do the deformation in the locally, that means you do not have the local limit, you do not have standard Minkowski. So if you, for example, if you study inflationary quantum fluctuations, you choose Bunch-Davies vacuum, imposing a Hadamard condition that in the short distance limit, you want to recover standard Minkowski. So if you do it differently, do you have a specific choice of vacuum which is different from Bunch-Davies? That could be some signature in primordial physics.
Yeah, you could think about it. I'm not aware of any work on this. You want to go?
System that
Ah.
does exactly what we're suggesting. You take Bose-Einstein condensate where you have this metric that depends on momentum because in annual gravity. And what they find is that basically there is a robustness of again of the Bunch-Davis vacuum because in a certain sense there is still an horizon, but there are modifications with respect to the standard inflationary scenario.
This is
Scale
nice.
dependent.
They have approximately that, but it depends on the comparison of energy. It's very similar. I mean, in many ways, it's similar to what I said yesterday about Gubitosi. It's a paper by Matt Visser, Silke by Furtner, and Gardiner. We're talking about 2003, 2004.
Okay.
Hmm.
Would be interesting. Any follow-ups?
Just go back to, I was searching the paper by Stepanenko and Aldenberger was curiosity. So it looks like Aldenberger group is called Aldenberger.
I think this is good.
Aldenberger tested the gravitational force, Newton law, up to 52 micrometers. While the paper by Stepanenko, if I understood correctly, they tested it up to 10 nanometers. Now, I don't know if that's more impressive. 10 nanometers.
Is it the name? I just have to confirm.
This Casimir, yeah, I can show it.
Well, I still have to confirm the name. AN?
Is that the force is now?
ADE. Adel. Okay.
It's a lot more, right?
Okay. But Adel? Okay, okay. I will see. Okay, one name. Okay, okay. Yeah.
Please keep the microphone on.
Please keep it on. Yeah.
Sorry, I think this is the one that Kelly was talking about. Blimey.
Yeah, it looks like it's below the micrometers. So.
Oh yeah, no, nanometers are.
But yeah.
Yeah. You send me the reference.
Yeah. Sure.
Thank you.
Why not we write the reference so that everyone gets the reference?
Yeah,
Yeah.
one by Stepanenko, it's 2003. Point 00948. While the one by other Berger is 2002 1176.1.
Okay. Anyway, reference for everyone. So
Thank you.
any further questions? Not, I will take again the opportunity. I have a question to Julia. So you in your talk you were mentioning about you want to measure any Lorentz violation due to by observing the time delay between the particles arriving at us from far distance. Of course, you are probing very high energy particles. I'm wondering, do you worry about some other physical effects which give signal of Lorentz violation in disguise, but basically it's not due to Lorentz violation, due to some other effect, maybe during the propagation of the particles, the particles encounter a lot of structures, or there is also local expansion, dark matter structures, whatever. So do you worry about those things?
Well, one good reason for using neutrinos is that they do not interact. So for
They
interact,
have dark matter that
well,
does not
they
interact as
interact
well.
weakly. We know that. So any other thing is not going to be is not going to cause a big effect. And above all, because so one reason for considering sources from a number of redshifts is that you can also test, if you see anything, you can check whether it has the behavior with redshift that you would expect if it was a propagation, Lorentz violating propagation effect or something else. So you can think about ways to disentangle possible competing effects.
And how many free parameters you have in the models you consider? That means do you have more observations to constrain the parameters and look at independent observations that can confirm or rule out your modification?
Well, the propagation effect, so in its most basic formulation, has only one parameter that is that dimensionless parameter that tells you what is the energy scale where it is becoming relevant. As for other things, so the main competing effect is due to delays that are produced at the source. So not during propagation, but it is the mechanism that is producing these particles that for some reason first emits one kind of energy and then another one. But this kind of effect, for example, you expect it not to depend on the distance of the source because it's something intrinsic of the source. So it will not scale in the same way with the redshift as this propagation effect.
And your sources are mostly AGNs?
Well, they're mostly gamma ray bursts.
Okay.
There are studies of propagation effects with AGNs and blazars that only use photons, not not neutrinos. There are fewer of these, but there are also some.
Follow-up from Anne.
When you use neutrinos, do you worry about the mass of the neutrino?
You can compute that it has an irrelevant effect. It's negligible.
Okay.
But it's true that the Lorentz violation could simulate the oscillation of the mass.
Well, that oscillation is another story. Is a full other story. Even the coherence can change oscillation. But these experiments, they are not sensitive to the flavor of the neutrino, for example. They tell you there was a neutrino, so you're not checking on that.
Can you distinguish whether neutrino came from like AGN or some supernova neutrinos? You can distinguish what kind of source emitted the neutrino.
Well, this is the big
okay.
questions that is bothering people working in astrophysics.
Okay.
Where do they come from? So this is a matter of current research.
Okay.
So far, there was a claim of, well, we know that they do come from supernovae because there was observation of a supernova explosion where we saw also the neutrino. So we do know that, but for other kinds of objects, it is still.
Okay. Any more? I have another question. In Bronstein cube, there is a corner which is non-relativistic quantum gravity. What does it mean? I don't understand this.
That's just the corner where you're sending speed of light to infinity.
Yeah, I understood
formally, but I don't know what was written there. What was in the original picture that I took, so I don't take responsibility for that. It's
experiments you were mentioning of quantum gravity in the light.
You
are an example.
but you are also. But it's also small gravity, weak gravity. So the corner, I think the corner you were mentioning was just, maybe I misunderstood which corner.
I'm
Relativistic and
non-relativistic quantum gravity, Planck scale,
So
but
I
non-relativistic.
think that corner was where speed of light goes to infinity and you still have the other.
Yeah, H bar
param-
and G. Yeah.
Yeah, these experiments.
you are up very fast.
No. You are in the C going to infinity limit, but you are also in the weak gravity limit. So it is not that side, it's a bit more towards actual quantum mechanics.
Maybe to explain the context of my question. So basically, in one of the dark matter models, like fuzzy dark matter, people take like Klein-Gordon equation, take the non-relativistic limit, you end up with the Schrodinger-Poisson equation. It is quantum, non-relativistic, but of course not really Planck scale physics. So is there anything like that in the Planck scale or still non-relativistic physics like we can think of, or maybe some?
So let me. So when you consider the formations of the physical theories we have, it's not that any deformation is quantum gravity. So you need to show that there is the Planck scale somewhere. So I don't know of this specific model, but it's not that any non-standard theory automatically is some limit of quantum gravity. You have to show where the Planck scale is.
Yeah.
Well, in situations, I mean, in the general field of supergravity, which of course should derive from quantum gravity and string theory and so forth, but maybe that's way behind. You have schemes of dimensional reduction which introduce their own scales.
Yeah, that.
Planck scale. For example, the purchases program on supersymmetry in large extra dimensions. That's exactly the interest of that it produces a different scale than you can look.
But wouldn't you expect that this is some intermediate scale that eventually you could link to the quantum gravity scale?
Well, in a sense.
It doesn't show explicitly, but I guess the expectation is that it does have some link.
In the sense that if it is, yeah, if it's eventually, for example, coming from string theory, yeah, but that can be a long way away.
Yeah, of course, of course. But to claim that it is a quantum gravity theory, it can be very hard to do, and as you said, a long way. But you should expect that eventually there is this link.
But not, I was just reacting to the fact that the Planck mass itself has to be front and center. It's not clear to me that that's the case.
Yeah, in some cases it's more explicit. In some others, you have to work out the relation.
I mean, from what I guess a lot of people have been talking about in this meeting involves, effective theories and so forth, which are kind of removed from the Planck scale in order to talk in some sensible way at lower energies where you don't have to go all the way. Asymptotic safety is sensibly the same thing.
Yeah, and indeed, I mean, you again thinking about that space of parameters, you can think about where your theory lies. So it is going to be some approximation maybe of the full thing, and you can think where you need to move to go there. That was the.
Maybe just to remind Kelly, so maybe Eric Birchoff working a lot on non-relativistic quantum gravity from string theory point of view, but well, it was never clear to me like where to apply for exactly non-relativistic quantum gravity. Although there are mathematical works when more string theory side on this.
I mean, the word non-relativistic came into this.
So well, I'm talking about that one of the corner of the Brownian cube. Yeah.
I'm just reacting to the scale.
Okay.
Discussion.
Okay. So yeah.
I mean, for example, just to emphasize a little bit more, this supersymmetry in large extra dimensions idea involved, for example, get down to 6 dimensions any way you want. Take the local metro, just get there.
and then start from that, and then with a dimensional reduction on the sphere down to 4 dimensions. And then there are flat space-times in 4 dimensions, looks like a nice starting place for building a home in. And then you break supersymmetry. Right, and then given the size of the sphere, there's a scale that comes from that. And then you say how much you want to break supersymmetry. We go ask people at CERN, you put in some sort of bounds from that. And then you find that the corrections, strangely enough, could be on the order of 10 microns, which is where all this Casimir stuff starts to come in. Somehow the numbers are not a million miles apart, but there's no mention of Planck. It's an intermediate set of scales, which may be applicable to observation and experiment. That's sort of from 10 years ago. I'm just quoting from some.
Yeah, but I mean, I agree that it may very well be that there are intermediate scales that for some reason become relevant. So that is, I'm not. I'm not opposing that.
There are some work from Mario Pujolas, non-relativistic quantum gravity. Considering this non-relativistic limit. Pujolas, non-relativistic quantum gravity.
Any further questions, comments? If not, let's thank Anne and Julia.